All right, hi everybody. We are going to do this lesson on 10.1.4, which is on something called summation notation. So that's what the focus is on. We're going to actually start by going back to the problem about Gauss, that mathematician who quickly added up all of the numbers from 1 to 100. So we're going to revisit that problem right here in 1050 Part A. So remember Gauss, the mathematician, whose teacher tried to keep him busy by asking him to add up the numbers from 1 to 100. Legend has it that Gauss did not show any of his work. Shocking, but he is commonly said to have used a method that starts with the steps below. Below, actually, to the right. So I tried to reformat this paper really quickly so that it was easier to do guided notes with. So your copy doesn't have the actual problems written out on them, but I wanted you to be able to quickly read along with me without the use of your book. Okay, so let's take a look at what the work here shows. So this is just part A is asking what is the strategy he was trying to use here. So if we look at this, what do we see? We see S, that's the sum of 1 plus 2 plus 3, 98, 99, all the way up to 100. And then we see S below it as well, except notice how it's different. It is actually written backwards below it. Why would he have used that strategy? So if we look and see that right here we get 2S, so we know that we're adding these two sums together. By flipping the second one backwards and adding the first terms, we get 101. 2 plus 99 is 101. 3 plus 98 is 101. All the way up to the end of the series, 98 and 3, 99 and 2, and 101. Every single of those values add up to 101. So what did he do? He added the series to itself, but rewrote it backwards the second time. How can we simplify? Moving on to B, how can we simplify the work that he started here? Well, we've got 101 plus 101 plus 101 plus 101 so many times. That means we could factor 101 out of this entire thing. So we would rewrite our equation as 2s equals, we factor out 101, and how many times are we adding 101 together? So think about that. We're starting with the first term. There's a 101 for that, all the way up through the 100th term. So there are exactly 100 of these 101s. So that would be 101 times 100. That would mean 2s equals, that product, 101 times 100, which is 10,100. Divide both sides by 2, and we get that the sum equals 5,050. So we have already computed this sum in a prior class, but here we just see how Gauss did it a little differently. So the interesting thing here is, how is this method that how is this method here, adding up the series to itself and then dividing by 2, how does that relate to how we've used the graph? So what I'm hoping you guys are picturing is the graph that we use that would have the sums next to each other. And then what we would do is split that in half and then rotate it onto itself to form this rectangle. What Gauss was doing was he was taking the series, so it would be this bar series that represented in the graph, and not cut it in, rather than cut it in half like we did, he would just put the entire thing right on top of itself, and it would be like this. So he was doubling it rather than cutting it in half. Then he would find the area of that by doing the length times the width, and then knowing that that was double of what he wanted, he would divide it by 2. So this method that we just looked at here is very similar to that rectangle method. He's just dividing by 2 in the end rather than dividing by 2 in the beginning, which is what we did. So it's just an interesting thing to look at. So we're actually going to do example D using his method. So What that means is we're going to add, we have got this new sum, s equals 2 plus 5 plus 8 plus 11, and so on, all the way up to 59. We see that from one term to the next, it's getting larger by 3. But let's just jump into Gauss's method. So he would have added this whole series to itself. So I'm going to add it to itself. But instead of writing 2 plus 5 plus 8 and so on up to 59, I'm going to start at 59 and then add, since it was going up by 3, I'm actually going to subtract 3. So that would be plus 56, plus 53, and so on down to 2. So it would be plus 5 plus 2. So in doing that, what's going to happen? So on the left-hand side here, we've got s plus s, so that's just 2s. And on the right-hand side, I've got 2 plus 59, that's 61, plus 5 plus 56, 61, 8 and 53, 61, all the way up to the end here, 59 plus 2, 61. So you can think of that 61 as the height of each of the columns if we copied and pasted the graph of this series on top of itself. So this is convenient because when we add the terms, each of them add up to 61. So up here then we'll have 2s equals, we can factor 61 out. So we're repeatedly adding 61, which is really 61 times however many times we're doing that. So we definitely need to figure out how many terms, what is the number of terms. So to figure that out, we need an equation for that series, a sequence that would generate this pattern. So let me switch colors to stay a little organized here. So if we're going to represent this pattern Tn, we are going up by 3, so that would be 3n. And my 0th term would be 2 minus 3, so negative 1. And I want to know what is n when that series equals 59, that last term in the series. So I'll quickly solve that by adding 1, and I get 3n equals 60, and then dividing 60 by 3 means that there are 20 terms. The reason we needed that information is because now we know that right here when we're adding 61 repeatedly, we are adding 61 20 times. So then we can finish the problem over here by writing 2s equals 61 times 20, or 2s equals 1,220, and then divide that by 2, and we get s equals 610. That's the sum. All right, so it's the same as that rectangle method, but we just did it in a little bit of a different order. We also could have done the number of terms, which is 20, divided by 2, which would be 10, times the height of the rectangle, which would be the first term and the last term added together. So it would be 2 plus 59, that's 61. The number of terms is 20, divided by 2, and then we would still get the same answer. Okay, so that's just kind of a little bit of an extension on things that we've already done in class. Now we're going to move on to this brand new concept of summation notation. So it's going to look a little funky. You've probably seen this symbol before, and now we're actually going to be using it. And it's hopefully not too intimidating. You've probably seen it before and thought it was super complicated, but this symbol right here, whoops, that symbol right there, just means to add up all of the terms you get. So let me break down this whole expression for you before we move on. Okay, so the symbol itself, it kind of looks like a backwards E right here, like a fancy backwards E. That is actually the Greek letter epsilon. I'm sorry, not epsilon, sigma. So we often call this sigma notation as well. So I'm just going to write that here. Sigma notation is summation notation. So this is the Greek letter sigma. It's the capital letter. And in math, what it means is the sum of the terms 1 through however many it tells you. So right here, I'm going to write on this a lot, so hopefully it's not too overwhelming, but this that I'm circling there is telling us to add up the sum of the terms 1 through 20. So this is a shorthand version of writing out an extended series that we've been doing where we have several numbers written out. So we will simplify this a little bit here. This letter C, a couple more things to explain. This right here is called the index. So the index is C. And that's just the variable that you're going to see inside of the summation. So this C means when C equals 1, we would plug 1 in there to find the value, and then we would plug in 2. The second term, plug 2 in for C. Then the third term, we would plug 3 in for C, and do that all the way up through 20, plugging 20 in for C. So this expression on the inside can actually be simplified a little bit. So what we're going to do is simplify it. So this is actually telling us to find the sum of the terms 1 through 20 of this. So when we distribute this, that's going to be, I'm just going to do the work right below here. This is going to be one colorful problem. Okay, so when I distribute my C, or my 3, it's going to be 2 plus 3C minus 3. And then I can combine the 2 and the negative 3. So this actually all simplifies to 3C minus 1. So that means when I'm simplifying that, I'm really finding the sum of the sequence 3C minus 1. Okay, so now I'm going to show you how exactly we take, what does this mean in terms of what we already know about a series. So now we're going to generate all of the terms of the series. Well, not all of them, but the first few. The first term of this series will be the value I get when I plug 1 in for C. And this is why I'm plugging 1 in, because this tells us what to start at. My starting value is 1. You can think of it as T of 1, my first term of the series. So I would do 3 times 1, which is 3, minus 1 is 2, plus the next term of the series. So now I'm going to be taking 2, so I go up by 1s here. So I started at 1. The second term, I plug 2 in. 3 times 2 is 6, minus 1 is 5. Plus, now I would take 3, plug it in for C. 3 times 3 is 9, minus 1 is 8. And even as we start writing out these values, we should expect the values to be growing by 3, right? Because we see 3C minus 1. So we know that we're adding 3 every time. And then since this has 20 terms, we can just do dot, 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 plus the last term, which we would get by plugging 20. This is always the last value we plug in. So 20, 3 times 20 is 60, minus 1 is 59. So this is what we've got. This is what the notation means. So hopefully it's not too intimidating now that you actually know what it means. It's just giving us a way to take these longer, sometimes tedious list of series to write out, and it's just giving us a shorthand way to represent it. So we don't have to write out all of the terms to represent the series. Okay, so let's practice using this in problem 51. So in 51, we're going to use summation notation to represent this series. Basically what we're saying is we want a shorthand way to represent the addition of these 1, 2, 3, 4, 5 terms. So that 5, 1, 2, 3, 4, 5, that indicates what this top number is going to be. This is always how many terms there are. So if we have 5 terms, that means we are going to find the sum. So we'll use the sigma from 1 to 5. So here's the thing that I forgot to say. This C can be any letter you want. It's kind of like the letter X. You could technically plug in any letter you want for a variable. So we don't have to use C. Let's say we want to use T. So we could say T equals 1. And I know that there are 5 terms. 1, 2, 3, 4, 5. So I'm going to go up to 5. Now we have to figure out what is the actual formula for this, because that's what's going to go on the inside. This is the formula we would have used for a series. I'm going to jump back up to this summation notation example. If I had just had this 2, 5, 8, and said what's the equation for this sequence, we would have done T of n equals, we would have seen, okay, that's plus 3, so 3n. And then what's the 0th term? That would be minus 1. So the formula for the sequence is exactly what's on the inside of the summation notation. So jumping back down to 51, this sequence here would be T of n. And let's look at how it's changing. We go 15, 19, 23, 27, 31. So that's increasing by 4. So plus equals, hold on here, equals 4n, and what is that 0th term? Well, if I go backwards, 4 from 15, that would be 11. All right, so if this is what's going to generate the series of these numbers, then, or this, if this green equation is going to generate this sequence of these numbers just with commas, then all I have to do is put that same equation here in sigma notation, and then that's going to mean add them together. So that means we would just put 4n plus 11. And that's it. Let's go backwards now in example B. So in B, we're given the summation notation, and we want to write out the actual series. What are the numbers, the actual values in this series? So we can see here how many terms are there. We start by plugging in 1, we end by plugging in 6. So that means there's going to be 6 terms. And we're just going to follow the rule. So the first number we're going to plug in is telling us right here, it's telling you to start by plugging 1 in. So this series, I'm going to write it out. So the series from 1 to 6 of t squared. So remember, this on the inside is telling us exactly what to do to each value of t. It's saying to square it. So that means this would be 1 squared, which is 1, plus, now I go back and change 1 to 2 down here, plugging 2 in, square it, that would be 4, plus 3 squared, which is 9, plus 4 squared, which is 16, plus 5 squared, 25, plus 6 squared, which is 36. So all we've done is taken this shorthand notation for a series and expanded it so we can actually see what the series is. And then to calculate the sum, we would just add all of those together. So 1 plus 4 plus 9 plus 16 plus 25 plus 36. You can use your calculator, or just trust me, those add up to 91. All right, so this is a pretty simple concept in terms of we are introducing new words and symbols here, but it's referring to a concept that you guys have already practiced with, which is adding arithmetic series. So we're going to turn the page and do a few examples together. All right, so we are going to calculate the series of each of these 4 arithmetic sums. So I want to start by reviewing the things that we need to know about an arithmetic series in order to find the sum. So if you remember, what we've been doing is saying that the sum of some nth term of a series is, we need to know the total number of terms because we're going to divide it by 2. And then we need to know the first term, t of 1, and the last term, and we're going to add those together. This is what I've been referring to as that rectangle method this entire time. So now I'm going to be giving you problems like this where I haven't written out the series, but I've just given you the formula for the series in summation notation. So we can quickly find out the first and last terms just by following basically this rule of telling us what to do. to generate terms of this series. So let's just start by writing out the first few terms of this series. Okay, so the first number we plug in is 1 because it says to plug in 1 down here. So I plug 1 in for 13 and I get 13 times, or 1 in for t, 13 times 1 is 13, subtract 5, and I get 8. The next term I would plug in is 2. I plug 2 in for 13, that's 26. I subtract 5 and get 21. The next term I would get by plugging 3 in, and so on and so forth, up to the last term that I would generate by plugging 10. Remember, this indicates the total, the last value, the last term. Plugging 10 in for t, so 13 times 10 is 130, subtract 5, and that's 125. So here I can see this written out in a little more of a familiar way. So the great thing is from this is we can easily generate the first term and last term, and we know the number of terms because we know we're starting at 1 and we're ending at 10, so that's a total of 10 terms. So now we can apply all this information to how we already know to generate or find the value of a sum of a series. So this would be, I'm going to use this notation. The sum of the first 10 terms of this series is total terms divided by 2, which would be 5, times the first term plus the last term. So this means S of 10 equals 5 times 133, which is 665. So this is the sum of the first 10 terms of that series. Okay, let's take a look at example B. So here we are given a series represented in the form of a graph. And keeping in mind the things that we need to know up here. When we look at this graph, this 1 here means we're at the first term and we have its value. This 23 here means there's 23 terms and we have its last value or that last value. So we already have everything we need to do this problem. So we know that, let's see, the sum of the first 23 terms is the total number divided by 2. So 23 halves times the first term, which is 105.5, plus the last term, which is 6.5. So 23 halves times 105.6 plus 6.5, which is 112. And you would compute that in your calculator, and you would get 1,288. So this was represented in the form of a graph, but we still can easily identify all of the needed information to compute the sum of that series. All right, so in part C, this one is different from the others because it's not specifying the value of n. Let me go back down here so we can see. So in this first one, we knew that we were stopping at 10. In the second one, we knew we were stopping with the 23rd term. And in this one, we start at 4, 10, 16, and go on to the nth term. So we're going to basically be generating a formula to compute the sum of the first n terms, regardless of what n is. So we still need the same three pieces of information: the first term, the last term, and the number of terms. Remember from class that when we were talking about something like this where it's not a specific value of n, but just n itself, remember that this 4 is the first term, 10 is the second term, 16 is the third term, and so on. So this last one is the nth term. So we have a total of n terms. So when we're finishing this problem, remember our answer is just going to be a formula, not a specific value, numerical value. So the sum of the first n terms here is our total number n over 2 times the first term plus the last term, which is 6n minus 2. And then we can just simplify. So this is n over 2, and then 4 minus 2. That's just 2, so I'm going to write it as 6n plus 2. And then we can even continue simplifying, because if we distribute this n over 2 times 6n, think of it as over 1, then our numerator would be n times 6n, that's 6n squared. And then we would take this and multiply it by 2. Think of it as 2 over 1 if that helps. So n times 2 is 2n, and 2 times 1 is 2. And I did make a mistake if you're confused here. I forgot to multiply this 2 by that 1. So this is 6n squared over 2 plus 2n over 2. And then we have our final simplified sum. Okay, so that would be 6 over 2 cancels, so 3n squared plus n. So this is the formula for the sum of the first n terms. All right, one last example here. So in part D, we're back to using summation notation. So again, we can see here the first number we plug in is 1, the last is 30, so that indicates that there are a total of 30 terms. We don't have the first and last term specified, but we can quickly find those out. So we can easily say t of 1, so if I'm plugging 1 in, that would be negative 5 times 1, so negative 5 plus 10 is positive 5. And then since I know there's 30 terms, I want to find the value of that 30th. So negative 5 times 30 would be negative 150 plus 10. So this last term is actually negative 140. So I have everything I need, and I can go ahead and write out how I'm going to calculate my sum. Not to the nth term, but to the 30th term, because we were told in the notation. All right, how will we do that? So the total number of terms divided by 2, that's 15, times the first term, which is 5, plus the last term, which is negative 140, so minus 140. So this is actually 15 times negative 135, and then we just use our calculator for that multiplication, and we get the sum of these 30 terms is negative 2025. All right, so hopefully you guys are following along with this. It's again, this sigma notation is may seem intimidating at first, but once you break down the meaning of it, it actually is a pretty simple meaning. So we'll stop here, and you should be good to go to finish your 10-1-4 homework assignment now.